and everyone who's joining. We're going to get started in just a minute. And in order to give him the full amount of time, we are just a little bit before the hour. So I'm going to hand it over to Ken, let him introduce himself, and then start his presentation. So thank you for being our presenter today, Ken.
Hi, everybody. Thanks for joining. And today we're going to talk about runoff water quality and how that can be improved from street sweeping. I need to start first kind of acknowledging my co-investigators, Elizabeth Fassman-Beck, who was supposed to be giving this talk today. I'm sitting in for her, and our other important colleague, Edward Tiernan. So we all work for the Southern California Coastal Water Research Project. You can find out all about our stormwater and other research activities at the website listed there. So listen, today I'm gonna hope that you learned three different things. The first thing is that cooperation and collaboration can lead to some great things, more than any one of us can do on our own. The second thing you're going to learn is how to construct and build and test, calibrate and validate a rainfall generator, a simulated rainfall generator. And then the third thing I want to teach you guys today, hopefully you'll learn, is how street sweeping can have impacts on not just what you measure in the sweeper itself, but on the water quality of the runoff when it rains. So hopefully you'll get those three things out of today. So let's move on to the first slide. So I work for this place called SCWRP, right? The Southern California Coastal Water Research Project. But today I'm actually representing the Southern California Stormwater Monitoring Coalition. You'll often hear me refer to it as the SMC. So there's the website if you want to go visit it. And if you go to that website, you'll see their mission statement, which I have written here. Really what they're trying to do is just do some proactive, prospective, research to try and manage stormwater better. Everybody has a lot of challenges in trying to manage their stormwater. And this is a group that's come together, both regulators and regulated, to try and, solve some of these really challenging problems. There's 18 agencies. Here's the list of them. Here on the left are the regulated municipal agencies and Caltrans. So there's 11 of those. And then the state and federal folks that regulate them. These are all members. And then our agency, we're kind of like the R&D arm of the group. So this is the folks that have been around for over 2 decades now, tackling all kinds of challenges. They kind of guide their way by creating these research agendas, and I just wanted to bring it up because this is the kind of gives a good kind of overview of all the different things they work on. So they create these research plans. They have a 5-year kind of vision to them, and they revisit it and reprioritize every year. So, and then they fund these projects voluntarily. So if you don't have a good project, it won't get funded. It's that simple. Most projects takes more than a year, so they do have some long-term vision, and they're trying to tackle problems that might be, kind of 2, 3, 5 years, even 10 years into the future. So very proactive group. The research agenda has lots of different things that they work on. I'm sure that you can relate to one of these types of categories, but today's work is really associated with BMPs. So they do both structural and non-structural BMPs. Kind of just took a quick look over the last 5 years. They've spent probably $1.5 million on this research in both contributed funds as well as in-kind services. And my guess is it'll be close to double that in the next 5 years. So why is the SMC focusing on non-structural BMPs? Well, the first thing is that for both the regulators and the regulated, non-structural BMPs are the best first option. You know, uh, those are, it's always the best way to go before you have to build stuff. Let's clean things up without having to build stuff. It's just way cheaper and hopefully super effective. Um, I think in other parts of the country, they might call them minimum control measures. They go by a few names, but this is always the first and best way to go. Here in Southern California, most of the regulated agencies, as they put together their watershed management plans, they assume that these non-structural things kind of can capture between 5 and 10% of their total pollutant load during wet weather. But there's not a lot of data to support that. So it's kind of what I would call a best professional judgment kind of a number. So that's why the SMC said, well, let's do some quantification, and you can see it was one of their highest ranked projects. So the real challenge is there's lots of different minimum control measures and non-structural BMPs. Which one should they work on? So they held a workshop. It included some literature review. They looked at all their different types of non-structural BMPs, and in particular, how they might use data from a research project to influence their, say, watershed management plans. And then they did a survey. And so I wanted to show you some of the survey results, because I think a lot of you might relate to some of these. The first one was pick your top 3 non-structural. Everybody got 3 votes. And here's a large variety of non-structural type BMPs. And of course, street sweeping, which is this one, is the one I want to talk about today. So anyways, I'm assuming that a lot of you will also relate to this type of data, which is, okay, once you have information on how well a non-structural BMP works, how effective is it at reducing loads? How are you going to use it? And you can see, at least in Southern California, they're going to use it to support things like their watershed management plans, their watershed models, factoring them into their total maximum daily loads in terms of pollutant removal. So, and trying to look at how it might change receiving water concentrations, which is really where the rubber meets the road in terms of compliance with their NPDES permits and compliance with the TMDL. So in your last talk, you saw John Ball talk about a lot of TMDLs and some pretty imminent deadlines. So maybe this is this will resonate with you and your municipality as well. And then the last thing that I wanted to show you is we asked them, well, which pollutants do you care about the most? And there's a few different ways to interpret this survey result. The way I interpret is they're all important. Somebody cares about at least one of them. So anyways, that's the results from the workshop survey and how they selected street sweeping, how they're going to use the data, and which pollutants they care about. I also said that kind of the SMC did a literature review. I'm not going to spend a lot of time on this, mostly because, you've had 2 previous speakers that did a fantastic job. I'm just going to kind of reinforce the things that they already told you. When we look through the literature, there's a lot of studies on what's in street sweepers. There's a lot of studies on like some of the pickup efficiencies, like you just heard, but there's very, very little information on how it affects the water quality in the storms following a street sweeping. So how effective was it at trying to reduce concentrations or loads in your actual runoff? And can we measure that? Uh, so, so this is just kind of reinforcing what you've heard from me and what you've heard from the previous speakers. The last thing is that, the new sweeper technology is better than the old technology, right? The new regenerative air sweepers work much better than the mechanical brooms. So the other thing I really wanted to emphasize is some of this part of the literature where people actually went to outfalls and swept versus unswept streets or something like that. And there's very rarely do they ever detect like a statistically significant difference. And that's for all the reasons, for those of you that do wet weather know the challenges, that there's a lot of storm to storm variability. So that makes it challenging to detect differences. And the other thing is there's a lot of surrounding land use, right? You get an outfall and it's never just a street, right? It's got all the surrounding land use as well. And so, so that kind of might dilute the signal associated with the street sweeping. So a lot of noise prevents some statistical determinations. And so that's what led to the next thing that I want to spend some time talking about, which is the SMCs, the Stormwater Monitoring Coalitions, their pilot project trying to evaluate street sweeping and its potential effect on runoff water quality. It's going to go in 3 parts. I'm first going to talk about the questions they're trying to answer and the study design that they're using to answer it. I want to talk about our prototype rainfall generator. So turns out that you just can't go to Granger and buy one of these things. And then I want to talk about our application of the prototype rainfall generator. And that way the SMC was looking at it is, does it show any difference? Maybe even in one of our worst types of streets? If it does, then we should continue to move forward. If it doesn't, then, let's move on, do something else. So this is a roadmap for the next series of slides, the next, 20, 25 minutes. So let's talk about the study questions. I already told you that the primary assumption in most of the watershed management plans, at least in Southern California, they assume that street sweeping removes about 5 to 10% of the total watershed load. This has really never been verified, not at least in rainfall, not at least in wet weather runoff. So there's 2 questions then pop up, which is, can we develop a reliable method to measure the difference in water quality between swept and unswept pavements when it rains? And we want to do this using field experiments, not models, not what we pull out of sweepers, but actually in the runoff, which is what people are regulated on. The next question is, what kind of pollutant load or concentration, how much reduction can we see due to the street sweeping? And just like in the survey, we measure a lot of things. Here's the generic kind of study design or conceptual approach, whatever words you want to use here. The idea is to isolate the street, not the surrounding land uses, just the part you're sweeping. So you really test half of a street that's swept and the other half that's not swept. That way you make sure you're having the same type of street materials, same type of traffic, those types of things. So that's pretty important. And then you want to standardize the testing conditions, right? The same type of rainfall, same intensity, same antecedent dry period, and the same sweeping techniques. So, and then to maximize our opportunity to detect the difference between the swept and unswept portions of the street, we wanted, at least in this pilot, to kind of pick a street we thought was going to have a lot of street dirt on it. I like that term from the previous speakers. So our initial scope was just starting easy and just doing one spot, swept and unswept with replication. All right, so I told you there were three things I was going to talk about in the setup. The first was the study design and the study questions, which I just went over. So let's talk about the rainfall generator, because that's the thing that's going to control for all the variability in the climate. And, that's the thing that really caused a lot of confusion in the literature during our lit review. So, by building a rainfall simulator, you can control rainfall volume or rainfall depth. You can control the intensity. You can control the frequency or the antecedent, the dry periods. You can control how long it's going to rain after it's swept. And you can control the exact catchment area. So, and make sure all of these things are the same from the swept to the unswept. And this is particularly true in arid environments like Southern California, where we might go 6-7 months without any rainfall at all. So, so the next handful of slides are going to be talking about the rainfall generator, because this is key, I think, to trying to test how, how we're going to measure the actual runoff concentrations and loads. So here's a picture of it being deployed. So I'll kind of describe it to you. The first thing is to look at where the water's coming from. We essentially fill up a very large tank with potable water. We'll run it through a filter and pressurize it so it's very clean before it turns into rain. And then the next part is to run it up through a distribution manifold. That's here along the top of this gantry. Then you use the nozzles to help produce the rain from the pressure. You can see these are located here on the bottom of these oscillating arms, because you want the arms to oscillate, because rain never falls in just the same place all the time. So, and then the gantry, especially with these wheels on it, makes it very portable. We have about 70 square feet under this rainfall simulator. It's about the size of 1.5 to 2 parking spots, essentially. So, and then the last part is how to collect a sample. And so we use some water bladders here along the curb face to make sure we don't lose any of the runoff. And then we'll use some peristaltic pumps to pump it into this composite collector. We essentially collect every drop of runoff that comes from this rainfall simulator. Sometimes I'll call this whole of storm composite or whole composite. But basically, we're not missing any of the runoff. So there's no inference from event mean concentrations or any of those kinds of things. It's the entire storm in a 55-gallon drum. So, and of course, all the parts are, kind of Teflon and those kinds of things, non-contaminating. All right, so I told you that you can't just go buy one of these things commercially. For what it's worth, there are commercial ones available, but they're typically very small and they're used for lab studies, and they might reign over 1 or 2 square feet. So, so the trick to building one of these for use in urban settings is that you need to have uniform rainfall coverage. You don't want it to be very spotty. You got to kind of target on rainfall intensities that we typically see in Southern California. And so kind of a heads up, foreshadowing, it's all about the nozzle you use and how much pressure you use. That makes all the difference in trying to simulate realistic rainfall. And then the other idea is how much energy the rainfall produces. So you want it to get close to terminal velocity, and that's really a function of the size of the raindrop. So these three things together are what can convince you that you're simulating nature. Um, I think the only thing to really emphasize on this is all these things like intensity and the energy of the raindrops are all the things that drive wash off. So if you haven't got these dialed in, you're not going to be simulating real wash off. So let's go a little bit deeper on each of these criteria or things we want to target. The first is the uniform rainfall conditions. And so here we are deploying this thing in our backyard. And so here's the simulator. And what you can see is these graduated cylinders. We line these up on these black dots. So across the entire grid under the rainfall simulator. And then we use that to generate this heat map. And the heat map is a function of rainfall intensity. And so the first thing you can see is here's our 70 square feet. The intensity we were targeting was about 1.25 inches of rainfall per hour. So for us, that's about a 25-year 1-hour storm. So a little on the high end, but that's for us around here. But that's what we wanted because we wanted to generate the wash off. And then the last thing is this coefficient of uniformity, which comes pretty close to what other folks are trying to simulate in the literature and what you might find just in natural rainfall. So uniformity, is it even across the surface? The answer is yes. Check. So the next thing was about raindrop size and the kinetic energy. Kind of the industry standard historically has been this thing called the flower test. For this, I have to tip my hat to Eddie Tiernan. I had never heard of it before. So, but it's a real thing. Basically, you fill up a pan of uncompacted flour. Essentially, you put it under the rainfall simulator for a very short amount of time. And then you can see the raindrops are essentially captured as little drops of flowers. It retains the shape and size. So it's really works pretty well. So then what you can do is sieve that and then be able to weigh or count the actual raindrops. And that's what you see in these little tin measuring cups. So what's kind of the results when you finish with that is something that looks like a graph, something like this. So here along the x-axis is the raindrop diameters, right? Based on the flower test. It starts at 0 over here, it gets larger as you go to the left. So, and then the y-axis is cumulative distribution frequency. So this is how frequently, either by count or by mass, do you get this size distribution. Now, the blue line is what we were getting from the rainfall simulator. So it turns out this orange line is what we got from a natural rainfall event. So, and so you see, they come pretty close. We were pretty happy when we saw this graphic that we're doing pretty good with the nozzle and pressure settings that we have to mimic natural rainfall raindrop size and their distribution. So just kind of summarizing, there were 3 criteria: intensity, uniformity, and energy. Here's what our targets were based on historical data or through the literature. And you can see we come pretty dang close. So we were pretty happy with this. So let's talk about application. Now that we've built this thing and we've convinced ourselves that it mimics natural rainfall, let's try it out. For those of you that are from Southern California, you might recognize this. This was in Long Beach. And this is where they'll be having some of the Olympic sailing in 2028. So this one's at the end of Junipero Avenue. And this red box represents where we did our study. Here's a close-up of it with a distance scale. And the first thing to do was create our event pair. Remember, we wanted to compare one swept to one unswept portion. And that's what you got on these separate sides of the parking lot. To actually do the rainfall simulation, to get enough volume, we literally had to rain on 3 different spots in the parking lot and then pull all of those together into a single whole of event composite. So say here on the swept area, here's the 3 spots where we took kind of sequential turns with the rainfall generator. It would fall into this gutter here, which flows towards this star, which is where we collected the composite. So, and here's the same thing, but on the unswept side. So each rain event, so like just this was about a 15-minute segment of rain. So it turns out that if you do much more than that, you're not going to be washing off more pollutants. You're just at that point starting to dilute your sample. So, and then the other thing, of course, is to add things like sample duplicates or equipment blanks. Make sure that, just standard QA kind of stuff. So we did this actually 3 different times. We did it twice, once in December and then a second one in December in this portion of the parking lot. And then we did it a second time on December 4th in this portion of the parking lot. So kind of summarizing again, you rain for 45 minutes, 15 minutes in each of these, collect this whole event composite, one on swept and one on unswept. And then we do that 3 different times. All right, so let me show this video. Hopefully this is coming through to you in Zoom land. So they have a regenerative air sweeper doing its thing. And then here's a picture of the swept versus unswept portions of the parking lot. Here's the same thing. I'm producing a video of the actual rainfall simulator here. You can see the gantry with the oscillating arms, couple of nozzles on each arm. And here's the source of the water. And over here with the blue is the filter and the pressurizing system. So here is the whole of composite sampling bucket. And you can see all of the rain is draining into the curb, and we're using the peristaltic pump to pump into it. think I did a reasonable job describing how this apparatus works. The main thing to know is that it might take longer. We would start generating rainfall pretty rapidly after the rainfall started. You'd start seeing the runoff, but it might last a little bit longer. And so we could then put in a multi-channel peristaltic pump and pump from all three of the different segments at the same time. So okay, well, the prototype system seems to work pretty well. Especially when you finish one, then you gotta kind of move it over to the next spot. That's what this video is trying to show. So the whole system can come apart. You put it in a trailer and take it to another street if you want. Break it down for storage. So it's probably one of the nicer parts of this is that it'll you can take it almost anywhere. And then this picture is meant to show how the sampling goes. So you have this 55-gallon drum of sample. You need to consistently agitate that either with a manual steering, or you can put it on a giant stir, a magnetic stir with a stir paddle. Either way, try to kind of homogenize the sample, and then you subsample for all the different things you want to measure. Here's the list of things we measured. So, including all the blanks and QA samples. And here's the results. So let me describe this to you. Each panel is a different pollutant type. So within each panel, we have a comparison of the unswept portions versus the swept portions. And then you have 3 dots, essentially 3 samples for each condition. And that represents the 3 different sampling events that we did. So 2 in December 4th and 1 later in December. And the solid line represents the average of the 3. And so the best way to interpret that is we'll just take total nitrogen. Here's the spread of data, but there's clearly a large difference between the concentrations or the mass, because it's all equal volumes, between swept and unswept. So you were going from 5.5 milligrams per liter, kind of on average, to 3 milligrams per liter, just based on the street sweeping, the single pass, after at least 2 weeks of antecedent dry period. So, and so you can see pretty much for all of these pollutants, the swept side is kind of consistently lower in concentration or load compared to the unswept part. And so, you know, for the SMC, this was illuminating. Everybody's eyes got real big. So, but then the next question became, well, yeah, but how representative are these, right? If we want to continue to move forward, was this just a really dirty area, or was this a really clean area? And so what we did was plot on top of this the interquartile distribution from the National Storm Quality Database, right? If you're not familiar with this, it'll be in the slide notes. It's a great resource put together by Bob Pitt and compiles municipal data from all across the country. And this gray box, the dots, the plots and the dots are exactly as the same as you saw in the last graph. All I've done is add this gray box, which represents the bottom is the 25th percentile of the stormwater quality database and the 75th percentile. And so what you can see for things like suspended solids, the trace metals, the bacteria, we're definitely in the ballpark of what other people see around the country. So on the nutrient side, we might even be a little on the high side. So there are no data for PAHs in that data set. So hopefully those of you from inside California and outside California are going to get a little stronger feeling for this now. All right, so I'm going to make this a little bit easier on you. And now I'm just plotting essentially the difference between swept and unswept. So we'll just take these conventional pollutants up here, like suspended solids and nutrients, coliforms, and basically all we did was the concentration difference between the swept to unswept. So anything that's in the positive direction is a removal. Anything in the negative direction is going to be essentially an addition. The swept is higher than the unswept. So I told you for each of these we had 3 replicates. The gray line is the average. So you can see for suspended solids were 10 to 15% type removal, load reductions in runoff. For the nutrients, we're kind of 25 to 45%. Coliforms, we're getting some pretty good removal on that. So, and even difficult things to treat like PAHs, we're still removing about 30% just with street sweeping. The metals was a little murkier of a story. Half of them have averages of above 0. So the way I'm looking at this is there's a couple of them that are clearly significant removal. Those tend to be the ones that are most difficult for most municipal stormwater programs, things like copper and zinc. You're getting some pretty substantial removals. Certainly more than 5 to 10%. The last thing I'm going to finish up on our pilot study is talking about microplastics. It came up once or twice in the previous speakers. It's one that folks are finding now frequently in untreated runoff. And it's becoming quite a concern, and people really aren't sure about how to clean stormwater for microplastics. And so so I wanted to spend a couple of minutes talking about this that we did in collaboration with our friends from the city of Santa Barbara. So same test sites. Here you can see the 55-gallon drum of our whole sample composites, right? Our whole storm composites. And we had 2 choices: run this all the way back to the laboratory and try to fractionate it. Instead, what we did was pump this through a sieve stack and just filter it in the field. So way easier, way faster. It prevents a lot of particle settling, microplastic settling, or agglomeration with other types of particles. So the main thing to know is that if you're going to do microplastic sampling, you have to sample large volumes. It's just that simple. So you can't just do 500 mils and say you've got a good representative sample. You have to do large volumes. So once you do get these in the sieve stack, now you can just bring the sieve stack back to the lab, and you can analyze those samples for microplastics, either doing particle counts on each of the sieves, or you can weigh them, or the other thing you can do is use some kind of advanced spectroscopic techniques using a Raman technique. That'll tell you what kind of plastic you actually have, polyethylene, polyurethane, so on and so forth. We did both. So the key thing to know is if you're going to do microplastic sampling, whether it's for street sweeping or anything else, you have to do a lot of blanks. And that's because there's a ton of background contamination. We've had to spend $250,000 just building our lab to measure microplastics to prevent background contamination in the laboratory. So in the field, we do these blanks of the water before we run it through our system, blanks of our sample after it runs through the system, sample blanks of just what's falling out of the air next to our sampling system, a lot of blanks. So we can talk more about this if you've got some questions. But here's some basic results. We have only one event that we did this with, and that's because analyzing microplastic samples is super time and resource intensive. Here's a picture of the microplastics just from the 63 micron fraction. This is also, these smaller fractions are the ones that are associated with a lot of the contaminant absorption. So the main thing to know is that anything above 355 microns, sweeping or not sweeping really didn't make a difference for this storm event. Their sweeping didn't help. But in these smaller size fractions where a lot of the contaminant absorption occurs, we do see differences. So here's at 125 microns, we're seeing a 71% difference between swept and unswept. And if you combine basically all of the smaller size fractions, sweeping can remove up to half the microplastic concentrations. So pretty impressive. This is some of the only data of its type available. So we were pretty encouraged. If you remember when I started this portion of the study and of the talk, I said there were 3 study questions. One, can we verify this 5 to 10%? That's the assumption going in. The second question is, can we develop a reliable method so we can get rid of the variability that's hindered all the literature up to this point and actually get statistically robust estimates of sweeping removals? And then what are some of those removal efficiencies? So, well, to summarize, here's the answers. So we are starting to verify this assumption, and we're thinking it might be much more than 5 to 10%. Now it's only 3 events on one surface, but I can tell you from the SMC's point of view, they're going to continue to invest in this because they think there's merit in continuing. So could we develop a method to reliably mimic natural rainfall for both swept and unswept pavements? We think we can. We can mimic intensities. We can mimic the rainfall drop size. We can mimic the energy. And we can do that over a very uniform surface. So we're pretty happy. I told you this thing's completely portable. So now we can move it to anywhere we want. And some of the pollutant load concentration reductions, just based on this one street sweeping pilot, we see removal of most of the things that they care about, at least in Southern California. Solids, we can get 25 to 45% removal for some nutrients. Some of the most important trace metals, we're seeing a 30 to 50% removal. For the organic contaminants like PAHs, we're seeing a 30% removal. And coliforms, much more. So, and up to half the microplastics. Now, remember, this isn't modeled removals. This isn't like pounds that we measure out of a sweeper device. This is what we measure in actual runoff, and which is the same thing that you'll be measuring for compliance with your municipal stormwater permits. So this is my last slide. where I'm going to talk to you about what we're doing next. Of course, we're writing up the results and preparing a manuscript on the actual device itself, which we affectionately call the squirt soaker. So you can build one for about $5,000. I'm putting the link here, so where we have a spec sheet and an SOP, and you can build one yourself for wherever you want. So the larger scale study we're scoping right now, we've had some agreement that we want to include factors like traffic amount, road surface condition, how often it's swept. We wanted to talk about different types of rainstorms, maybe more frequent, less frequent, more intense, less intense, more volume, less volume, and then something about the sweeper operation. So the main thing to know is that we're looking for collaborators. The SMC judges itself on how many external collaborators they have on their projects. So we welcome non-SMC folks to participate with us. Maybe we'll do it in your neighborhood. So maybe you want to add some more concentration measurements. Whatever you want to do, add a little bit. The collaboration makes for a bigger, better project than any of us could afford all on our own. So anybody that's interested in collaborating, wants more information about the SMC, about the rainfall generator, or about our pilot application, I encourage you to contact Elizabeth, and here's her contact information. So that completes my presentation.
Fantastic, Ken. Well, we have a question in the chat, and while we are waiting for any more questions to come in, feel free to use the chat function, but here's the one that's already come in. I believe you use the intensity of a 25-year event. Are you able to adjust your rain machine to have an intensity closer to a 1 or 2-year event to understand the benefits during a more typical event?
So we're working on that. Know that most rainfall simulators and most nozzles associated with rainfall simulators, they're targeting typically very intense events because they're typically looking at erosion. And so, yeah, and they're looking at, events in other parts of the country, typically the more agriculturally dominated portions of the country. So, that being said, we are trying to get intensities that are a little bit lower. So, and for that, we've actually looking to make custom nozzles using 3D printing technology.
Fantastic. Is there any more questions? There are. You can either unmute yourself or you can put them in the chat.
I could make a comment or two. Excellent job, Ken. Thanks so much for making that presentation. I think someone asked, well, about what your future, why this isn't posted, and you covered it. You now are going to take this out into the real world, and you're going to start simulating rainfall on real streets with real street dirt, with and without street sweeping. So, I mean, it's going to be pretty exciting when you do that. What you'll find, I think, is that if you generate enough and long enough, make sure you got big enough bucket, you are going to actually increase the wash off, because gutter flow is much more effective in terms of its ability to pick up and transfer downstream sediment, especially of fine sediments. And if you've removed the armoring, as is the case with with the regen, it gets both fractions, then you're going to see a much better simulation. I was like your metals, for example. I think the only way I can explain it is that you're right now simulating overland flow. And generally speaking, that's a third effective as gutter flow. So I think that'll be the challenge, is is generating enough gutter flow, but I'm really pleased with what you guys are doing. This is very exciting. And, what if this were to be combined with the actual sweeper test? Instead of us just vacuuming up, what if we went out there with rainfall simulator and simulated what was left and let that wash off? I think that could be pretty powerful. Much more expensive, of course, but it's a possibility. So I'll stop talking now. Thanks.
I think that'd be a fabulous idea. So I'm all for it.
And Ken, since I'll say that too, Roger and I have been texting each other saying, talking about what a great combination this is and a wonderful addition to our toolkit. So congratulations and nice presentation. Thank you.
Fantastic. And it looks like we have another question that just popped into the chat. Given that there are some differences in aggregate and paving, hold on, chat just moved. Could the makeup of the concrete or asphalt substrate have any effect on the concentration measurements of pollutants or constituents? Did the research take this into account, or could future studies?
Yeah, so that's a great question. And we all presume that the street surface type and its condition, like whether it's rough or smooth, like some of the previous talks, will make a large difference. It'll make a large difference on the types of particles that will land there. It'll make a difference on how well it can be swept. It'll also make a difference on the rainfall amount that it's going to take to wash off the pollutants. So, yeah, I think that's an astute observation. That's what we're going to plan to tackle in the next phase as we implement, is to really test how much of a difference does it actually make. So, and actually do some actual quantification of that.
I think when you think about accumulation, most of the accumulation in the real world is happening in gutters, and most of the gutters are concrete. The asphalt interface ends at that gutter lip. Sometimes that can create an opportunity for material to accumulate, making it difficult for the sweeper to get to, but much easier for the water quality flow to get to at the gutter flow. So I've never really seen any data of concrete versus asphalt. I don't think it's a huge difference maker. I think it's all about the wash off and the gutter flow aspect, which makes it much more complicated.
Okay, I'm not seeing any more questions, so we might let everyone off a couple minutes early to go get some lunch. But thank you so much, Ken. This was a fantastic presentation, and thank you everyone for attending. We hope to see you at the remaining 3 Stormwater Awareness Week workshops. Yeah, we only have 3 left for this week, so we have one starting in just a couple of minutes. That is SWIP Radio and Stormwater World Podcast together live. They're going to do live podcast, and they're going to be talking about AI and stormwater, technology and stormwater. What does that look like? AI is a force to be reckoned with now, and so they're going to test and see if AI can write a stormwater pollution prevention plan. So you might want to check that out. Then we have the 5 fundamentals for developing sustainable vegetation on construction sites. That's at 1 p.m. Pacific time. And then finishing out the week, we have National Nightmares, eerie episodes from the water calamity crypt. That one's going to be a really interesting and fun one. So that's at 3 p.m. Pacific time. So we hope to see you at the remaining workshops. So thank you, everyone, and thank you, Ken.
Thank you, Rebecca, Ranger, and Roger, too.